Hello everyone, welcome to the module on stereochemistry. We are still continuing to discuss the arrangement of atoms in space in a molecule and what are the consequences or the properties thereof. So, we will continue this discussion in this lecture, and in this lecture we will look at a bit more closely what are called as enantiomers and diastereomers, the different properties and possible applications. Before we get into enantiomers and diastereomers, let us just first briefly recap what we discussed in the last lecture. In the last lecture we said that symmetry and chirality of a molecule are related to each other, and a molecule is said to be chiral when there is no improper axis of symmetry, that is Sn in a given molecule. So, just to reiterate, if we take a molecule, the earlier definition or the earlier proposition what we had discussed was, if a molecule is attached to 4 different carbon atoms, we called it a chiral center, which is indeed not incorrect, but not fully correct either. So, to have a complete definition or a definition which captures a large class of molecules, what has been done is to look at the relation between symmetry and chirality of a system, and it is concluded that a molecule or a system which lacks improper axis of symmetry, that is Sn, is said to be chiral, and we looked at some examples of this in the previous lecture. And a consequence of this is that I could have a molecule, for example tartaric acid, or the one we discussed in the previous lecture, that is 1,2-dichloro-dibromoethane, where you have more than one individual chiral centers, but the molecule as a whole or the molecule in totality is optically inactive. So, this is a consequence of the relation between symmetry and chirality. So, this is a very key distinction which one needs to keep in mind. With this, now let us get into looking at what are called as enantiomers and diastereomers. So, we again go back and try to look at this example of 2-methyl-butanol, which we looked at in the previous class. So, here what we have is one carbon atom, which is the one which is the pointer is showing now. It is connected to 4 different atoms, and it also lacks the Sn improper axis of symmetry. As a result, this is a chiral molecule, both of these are, and the relationship between them is that they are non-superimposable mirror image of one another. I will repeat again, these are non-superimposable mirror image of each other, similar to our hands. So, as a result, we call these 2 sets of molecules, that is R2-methyl-butanol and S2-methyl-butanol, as enantiomers, and they always come in pairs. Like you can see here, if I have a carbon atom which has a methyl group which is coming up, a counterpart of that would be the methyl group which goes into the plane of the screen, and that would lead me to the S enantiomer, correct. So, this is a very simple case of when we have one atom or one carbon atom which has 4 different substituents or which lacks a symmetry. Now, what happens if I go to a system which has more than one chiral center? Now, let us take the example of this 1-ethyl 2-methyl cyclopropane and look at it in a little more detail. So, here what I have is, I have 2 carbon atoms which are chiral. So, I am just going to mark them with an asterisk, that is this particular carbon and this particular carbon. So, a rule of thumb is that if I had just one stereocenter, then I got two two stereoisomers which we call them as enantiomers in the case of 2-methyl-butanol, like for example here. However, now we have two chiral centers in this particular example. So, in such a case, what is known is that the number of possible stereoisomers is given by this formula of 2 to the power n, where n is the number of chiral centers. As a consequence, you could easily say that if I have 2 to the power n, so then it would be 2 to the power 2, so it would be, I would expect 4 stereoisomers of this, correct? So now let us look at what are the different possible stereoisomers. So I have drawn here the 4 possible stereoisomers of this molecule. So let us go one by one and look at them. So if we start with the one on the left, that is the molecule SS, what you see is that the methyl is first actually pointing into the plane of the screen and the ethyl is actually coming out. And what is done in the molecule 2 is exactly the opposite, that is you have the methyl going into the plane and the methyl is actually coming out of the plane and ethyl goes into the plane. And so on and so forth, we can just vary the disposition of this methyl and ethyl and we would end up in these 4 combinations, correct? And so now we have 4 set of stereoisomers. So now let us go ahead and try to visualize them and try to understand from this what are enantiomers, which we have partly understood, and also look into what are diastereoisomers. To do that, what I would do is I would again go back to our molecular models and take the help of molecular models. So here I have constructed a molecular model of a particular system here, which I would begin by showing it to you. So this is the cyclopropane system is what I have constructed. So this is I am trying to show it as a structure 1, the one on the extreme left, and what you see here is that I have a CH2 group which is exactly same as this particular CH2. So that's this CH2 is what I am trying to show here on this left. This is the carbon which is the CH2, and then I have this carbon which has a CH which is coming towards me and a methyl group. I am showing the methyl group by a red ball here. So this could be any substituent, and this is the one which is actually going down. So let us call this the green, right? And if I actually now come down, then I have the ethyl group which I am showing it by the red ball here, and the red ball is actually coming towards me. So I would call this red just to keep track of the colors, alright. So I have this particular enantiomer or this particular stereoisomer which I have made a model of, and I hope everyone can see this from this particular model. And now what I will do is I will go to the second one where I am again holding it in the same kind of a position as that of 2, structure 2, and you can see that the CH2 is here, which is the one which you can see here, the CH2, and now the green ball which is actually the one which was actually going down is now coming up, correct? That is in accordance with what is drawn on this board. So it is actually coming up if I hold it like this, and the CH is going into the plane of the board. So now this is the green is actually, now I have put the green as coming towards me or away or out of the plane of the screen. And if you now go and look at the ethyl which is the red one, so this is actually now going into the plane of the board, and that is in accordance with the structure 2. So I am just going to draw this as red, right. So I will just hold these two again, right. So I have just these the same two structures, I am just holding it again here to show you from two different perspectives. This is structure 1 on my left hand, and on my right hand is the structure 2. So to look at the relation between the two, what I would do is I would just hold them like this, and I am just holding it in just a different conformation on my hand, I am holding it like this and I am going to just flip this guy, and I hope you can see that the one on the right, the molecule on my right hand is actually a mirror image of the molecule on my left hand. If you draw a mirror plane just in between these two, then you would see that these two are actually mirror image of each other, right. I hope everyone sees that, because you have the green balls which are actually kind of mirror images, the reds are mirror image, and you have the hydrogens are also mirror image for both of this. So once you have the mirror image, what we need to now next look at is try to see if these are superimposable. So let me try and put one on top of each other now. So I am trying to put one on top of each other. So here what I have been able to do is, in this sort of mashed geometry, I have been able to put the red ones together. I have the red atoms are actually coinciding with each other, but you can see that the green is now on top of the white, and similarly here the white is on top of the green. So that means these are actually non superimposable mirror image of each other, 1 and 2. So what that means is that the structures 1 and 2 are enantiomers. So I again reiterate, structures 1 and 2 are enantiomers. So let me just write here. Enantiomers 1 and 2. So this is one pair, and you can do a similar exercise for, let us say, molecule 3 and 4, where I hope you can see that the absolute configuration is exactly opposite in this case. Like the carbon bearing the methyl has an S in 3, whereas it has a configuration of R in the 4, and similarly it is R in the case of 3 and it becomes S in the case of 4. So that means these are again a pair of enantiomers similar to molecule 1 and 2. You can again convince this yourself by making a models like this and then trying to superimpose them or look at their mirror images. I will just, for the sake of convenience, I will write here that both 3 and 4 are also a pair of enantiomers, correct. So now we looked at two sets, that is 1 and 2, 1 and 2, and we also looked at the relation between 3 and 4. So now the question is, what happens if I look at with respect to 1 and 3 or 1 and 4 or between 2 and 3 or 2 and 4. So that is the interesting bit. So let us try and do that now. So let us try to compare 1 and 3. Okay. So now I am going to compare the structure 1 with the structure 3. So I go back to my first structure here, that is the CH2 is intact and the green or the methyl is actually going into the plane and the red or the ethyl is actually coming out, right. So I keep this structure intact, and in order to make the other structure, that is the structure 3, I am going to just tweak around this a bit. So this was actually my 2, I would like to make this into a 3. So for that I have to just juggle a bit. Okay. So now I hope you guys can see this now. The model which I am showing you is the model of structure 3. So here you have now the green, which is again pointing into the plane of the screen, and you have the red, which is the ethyl, which is also pointing into the plane of the screen, like in this particular case here. This is green and this is red, correct. So both are actually going into the plane in this particular example. So now what I have is, I go back to this molecule, that is molecule 1, and I have molecule 3. I am just going to hold them back here like this, similar to what I did with molecule 1 and 2. So now what you see is that if I actually if I try to play around with this, if I try to, let us say, do a similar trick, if I rotate it, actually these are not mirror images. If you carefully look at them, you see that the red atoms are in accordance with what would one expect, but the green atoms or the green substituents are actually not. So, as a result what you see is that the 1 and 3 are actually not mirror images of each other. I hope this is visible, because you can see the red balls are actually in correct relation what you would expect, but the green ones are actually off. So, what this means is that structure 1 and 3 are non-mirror images, and now let us look at if they are superimposable. So, I am going to just put them one on top of each other, and so what you see here is that I have the white or the CH2s I am able to match, which is this particular carbon to the left, whereas the carbon which has the red and the green balls are actually not on exactly on the same, they are actually offset. So, what this tells you is that these structures are non-superimposable and also non-mirror image of each other. So, I again reiterate that structure 1 and 3 are non-mirror image, that is the first point, and they are also not superimposable on each other. So, what these kind of structures are what are called as diastereomers. So, I am just going to write down here. So, structure 1 and structure 3 is a pair of diastereomers. So, that together constitutes one pair. You can do this exercise similarly, and what you would see is that the structure 1 and the structure 4 is also a pair of diastereomer, because here you see that the on this particular on structure 1 this is S configuration, and here on this structure 4 it is S configuration, but if you go to the other carbon it is S, whereas here it is R. As a result, I would write down them as 1 and 4 also form a pair of diastereomers. With the same set of arguments, you can compare now 2 with respect to 3 and 4, and what you would see is that 2 and 3 are again a pair of diastereomers, because both the stereocenters on each of them are not exactly same, that they are not exactly opposite. As a result, they are not enantiomers, but they are diastereomers. So, you would have 2 and 3 as a set of diastereomers, and you would, if you go and compare 2 and 4, you will again see the same relationship, that is they are non-mirror image, non-superimposable one on top of each other. So, that would mean that 2 and 4 are also a pair of diastereomers. So, I hope till now it is at least a bit clear that what do we mean by enantiomers and what do we mean by diastereomers. I will again reiterate, enantiomers are mirror image of each other, but they are not superimposable one on top of each other, okay. Whereas diastereomers are non-mirror image and also non-superimposable on top of each other. So, that is the key but a subtle distinction between enantiomers and diastereomers. So, let us try to concretize this distinction between enantiomers and diastereomers. So, the first one is that, as I told you, enantiomers are non-superimposable mirror image of each other, whereas diastereomers are non-superimposable non-mirror image of each other. So, they are also not mirror image of each other. And another important distinction is that in the case of enantiomers, we have what is called as both the systems have opposite chirality. That is, if we took two systems, the chiral centers at each of the points are actually of opposite configurations, whereas in case of diastereomers, not all stereocenters be of opposite configuration. There can only be some which are of opposite configuration. That is also a very key distinction between enantiomers and diastereomers, like we saw in the previous slide. And finally, a consequence of that is, we know that enantiomers typically are having almost exactly the same physical and chemical properties, except the way they rotate the plane polarized light. That is, they rotate to the to the right or to the left. However, once it comes to diastereomers, the properties of diastereomers can be distinct. That is, they can have different melting point, different boiling point, and so on and so forth. So, that is a very key attribute of diastereomers. Alright. So, this all looks nice and very sort of academic and textbook kind of stuff. So, then some of you might be wondering, is there any application to this or is this of any use? So, let us go ahead and briefly look at one of the application of these concepts. So, here what I have tried to do is I have tried to show you a 1,2-diaminocyclohexane system. This is a particular one is a cis, but you can also get a trans, then you will have both enantiomers possible. What is known is that these kind of molecules are actually have a wide range of applications, like in chiral catalysis, that is the drugs which we take nowadays, for example for COVID or for any other ailments, these drugs are invariably having only one of the configuration, that is R or S of a particular stereo center, and it is very important to have it in a high purity, that is the R should be in extremely high purity, which is also called as an enantiomeric excess. So, there is a huge field in which people are interested in making a given enantiomer or diastereomer of a molecule with almost exclusive purity, so that you do not have other diastereomers or enantiomers, and that is important for their ultimate biological activity. So, in this context, what is known is that these kind of molecules are actually very good catalyst to synthesize a given small part of a drug. That is one of the application, and another important application is something called as an organogel. If you haven't come across them, you can visualize them or think of them as a toothpaste which we all use in the morning. So, these are actually very soft materials which can have various kinds of applications. So, these materials are also useful as organogels and various other applications. So, now where comes the problem? So, the problem is as follows, that if you want to use these particular molecules as either chiral catalyst or as organogels, one should be able to have them in very high enantiomeric purities. That is, I should be able to have exclusively SS or exclusively RR derivatives. However, commercially obtaining them is actually a bit expensive, whereas if you really look at commercially, the 1:1 mixture is very easy to get, because that is more easily available, and it is very hard or it is economically not viable to separate a mixture of enantiomers into their separate components, that is 2 enantiomers. So, it is in this context or this problem of separating a 2 enantiomers from a racemic mixture, or also called as optical resolution, is where diastereomers can be of extreme utility. And let us see how they can be of utility. So, here is a very simple idea which actually was published in about 2 decades ago. So, here what the authors have done is, on the left I have a mixture of both the enantiomers, that is I have a racemic mixture, and to this racemic mixture they add L-tartaric acid, that is a 2R3R derivative, which is also commercially easily available, and once you add this, they observed 2 kinds of products. So, what happened is, the 1R 2R derivative of the cyclohexane actually goes and complexes with the 2R 3R tartaric acid, and this interaction between the cyclohexane and tartaric acid is very strong, because they have a match in chirality. If you look at the chirality here, the cyclohexane has a 1R 2R and the tartaric acid also has a 2R 3R. As a result, they have a very favorable configuration to interact with one another, thus they interact strongly, and once they interact strongly they form a precipitate, and then the solubility product diminishes and they crash out of the solution, or they are insoluble. However, on the other hand, if the 1s 2s derivative of the cyclohexane actually does not interact so strongly with the 2r 3r, just because of the way in which the groups are arranged spatially. That would be evident if you build a space filling or if you build a molecular model like this. So, a consequence of this loose interaction between the cyclohexane 1s 2s derivative and the tartaric acid is that they still remain in solution as a weak complex. So, the solubility of the solubility product of this complex does not overcome and it does not crash out. So, thus what I mean is that this particular product, which is the 1r 2r complex with the tartaric acid, actually crashes out as a precipitate or as a lumps, whereas the other enantiomer actually still remains in the solution. So, once you have this, then all you need to do is to go back to lab and just filter this out, then you are now left with a pure 1r 2r complex with the tartaric acid, which can be further easily decomplexed to get a pure derivative of 1r 2r 1r 2r diaminocyclohexane. So, with this simple experiment, what we are trying to say is that these diastereomeric complexes, that is the interaction between the diaminocyclohexane and the tartaric acid, is a diastereomeric interaction, and similarly here between the 1s 2s and the tartaric acid is a diastereomeric interaction, and this diastereomeric interaction is what ultimately governs their solubility product and also the way in which we can actually resolve them. I hope this has given you at least an idea of how the idea of diastereomers can be used for optical resolution as one of the applications. With this, we will stop here and thank you for listening.